Before explaining the definitions of symmetry, let me just show you a couple of graphs so that for you to find it is going to be by intuition. For example, I have this drawing. This is obviously not a function because it fails the vertical line test, but it's a relation that it's being graphed. And actually you can appreciate that it has some symmetry. If this was a face, then you can see how the x-axis is going through the nose and is splitting this face into half, and each half is they are identical. So in this case, the graph of this relation is been said to be symmetric respect to the x-axis. So the only thing that it means is that if I were to fold this relation over the x-axis, the graph of one side completely overlaps the other side. Okay, and if this paper was transparent, you probably can see it easily, but you can see that you don't see any other marks over here, so it does overlap completely. So this graph is symmetric respect to the x-axis. So whenever you have a graph that is symmetric respect to the x-axis, for any points that are correspondent, like for example this point here, the corresponding point will be over here. If I have coordinates, let's say I'm estimating 1.52, the coordinates of this point will be 1.5, -2, and that will be true for every pair of points here on this graph. Therefore, you notice how the x coordinates stay the same, but the y coordinates are opposites of each other. So for any graph that is symmetric respect to the x-axis, the x coordinates are the same and the y coordinates are opposite of each other. Now we're going to appreciate different characteristics about other graphs that are symmetric to other parts. For example, this one, this graph is symmetric respect to the y-axis because I can do the same thing. I can fold it over the y-axis and I can see that half of it overlaps with the other half. This graph will not be symmetric to the x-axis because if I were to fold it over the x-axis, you see how one part of it does not overlap with the other half. So this graph is only symmetric respect to the y-axis. So this is the way we will write in symmetric respect to y-axis. And then let's look at what happens to two corresponding points. If I have this point, the corresponding point over here will be this one. So if the coordinates of this point, let's say, is 3, 1, the coordinates of this point -3, 1, then what you can compare here is that the y coordinates are the same, however the x coordinates are opposites. So for anything that is symmetric respect to the y-axis, the x coordinates are the ones that are opposite and the y coordinates are the same. And this is a nice conclusion that we're going to use later on. And then the other type of symmetry that we're going to talk about in this section is symmetry respect to the origin. Now this is something that is probably going to be a little bit harder to see, the origin being the point 0, 0. So what this means is that anything that we may have graphed on the first quadrant is going to be actually repeated on the third quadrant, and anything graphed over here is going to be repeated over here. So how can I check for symmetry with respect to the origin in this graph? Well, let's say that I'm tracing the part of the graph that is on the first quadrant. I put my pencil on the origin, and then what I'm hoping for is that when I rotate around the origin, that this piece overlaps with the other piece. And it actually does. Okay, so this is what we refer to symmetric respect to the origin. This piece will overlap this piece. If I trace the bottom piece, then it will overlap with the one from the first quadrant as well. So this has symmetry with respect to the origin. Now, if you check for symmetries about the x or the y-axis, you will see that they don't overlap. So this is not symmetric with respect to the x-axis, and this is not symmetric with respect to the y-axis. So the only symmetry that it has is respect to the origin. And now let's look at what happens to the coordinates. So the coordinates of this point will be 3, 2. And then the corresponding point here is over here, and it's -3, -2. So the x coordinates are opposite, and the y coordinates are opposite. So x coordinates are opposite, and the y coordinates are opposite of each other as well, whenever a graph has symmetry with respect to the origin. So let's read about our summary here, and now let's see if it makes sense. It says symmetry with respect to the x-axis. So remember that if that's the case, I can make the fall through the x-axis, and those two pieces should overlap. So it says how to test for symmetry. The equation is unchanged when I replace y with -y, which means if you either have y or -y, you should have the same x as answer. So it says what the graph looks like. It may look like this, or it may look like that. Anything that is symmetric with respect to the x-axis works. And it says graph is unchanged when reflected in the x-axis. When I have symmetry with respect to the y-axis, then you know that the x's are opposite and you get the same y's. So the equation naturally is not going to change whether I have x or -x. And the graph is unchanged. And then symmetry with respect with the origin, the equation does not change whether I have x or -x, or y and -y. And you can see how to obtain points on the other side of the graph, the only thing that I have to do is change, find the opposite of the x coordinate, find the opposite of y coordinate, and I'm going to have points on the other side. So let me just give you an example before the examples from the book to clarify that. So one thing that you know that definitely has symmetry respect to the y-axis is y equals x squared. You know that the graph is a parabola that has a vertex on the origin. Okay, so you know that that's symmetric respect to the y. But when we have to test for symmetry, that means using algebra show me that this is actually symmetric with respect to the y-axis. So when I'm checking for symmetry with respect to the y-axis, what I'm hoping is that whether I have -x or I have x, that the equation remains the same. So instead of x, replace x with -x and then see what happens. So when I do that, the function is y equals x squared, and now I'm going to have y equals -x squared. Now remember that whether I have a positive or a negative number squared, that always gives me a positive answer. So -x squared is nothing but -x times -x, and -1 times -1 is 1, and x is x squared. So when I replace x with -x, it gave me the same equation that I had at the beginning. So when I do that, I say this is symmetric respect to the y-axis. Now, what if I have x equals y squared? This is not a function, this is a relation, and the graph looks like this. So I know that this is going to be symmetric respect to the x-axis. But how do I test? The test will say, okay, replace y with -y and see if you get the same equation. So I'm going to take my equation and I'm going to replace y with -y and see if I get the same thing. -y squared is -y times -y, and that is y squared, which is actually the same thing that I had before. Since the equation is unchanged, then I say x equals y squared is symmetric respect to the x-axis. Now let's say that I have another function y equals x cubed, and you know the graph of that looks like a snake. Now I want to test for symmetry, so I know that this is going to be symmetric respect to the origin. So when I test, you have to replace y with negative y and x with negative x and see if you get the same thing. So y gets replaced with negative y and x gets replaced with negative x. So now you have negative y equals, this is negative x times negative x times negative x. Now negative times negative is positive, times negative is negative, x cubed. Now remember that negative y is negative 1y, so when I divide both sides by negative y, you get y equals, these two negatives will cancel out, and you have y equals x cubed, which is actually the same function that you started with. Since the equations remain unchanged, since replacing these two at the same time didn't give me a new function, it gave me the same, then I say this is symmetric respect to the origin, or about the origin. Okay, if you got something that is different from the original, then that function does not have symmetry respect to whatever it is you are testing. So now let's do the example 11 and 12. It says test the equation for symmetry and sketch the graph. Well, first I want to test for symmetry, because symmetry actually makes my life easier whenever I have to graph. So I'm going to test for symmetry respect to x-axis. So for that I change y with negative y. So x equals negative y squared, and you know that that doesn't change. So I get the same equation, so that means that it's symmetric respect to the x-axis. Then I don't have to test for anything else. I don't have to test for the other ones, because I know my graph is symmetric respect to the x-axis. So the only thing that I have to do is now pick a few x's. So I'm gonna pick, I don't know, 0. Oh, sorry. I'm gonna make a small table. I'm gonna pick 0 and 1 and 4. So how much is y in those cases? When x is 0, then y is 0. When x is 1, then it becomes 1 equals y squared. So I have y is 1, or y could be negative 1. So this is 0, 1, 1, and the other one. Because you know that since they are symmetric, if you have one point, you can just reflect it over the x-axis and you have another point for free. And then when x is 4, that's y squared, x could be 2 or negative 2. So you have this other point for free. So you can graph these points and then reflect them over the x-axis, and you have these other points for free. Now example 12 says, using symmetry to sketch a graph. You don't know whether this equation is going to be symmetric respect to the x-axis or the y-axis or about the origin. So let's test for symmetry respect to the x-axis. For that you have to replace y with negative y. So when I do that, I have negative y equals x cubed minus 9x. Now I have to divide by negative 1 both sides, so I have y equals, this divided by negative 1 is negative x cubed, and negative 9 divided by negative 1 is positive 9. Now you ask yourself, is this equation the same as the original? And the answer is no. The signs are different. So is it symmetric respect to the x-axis? So the answer is no. Not symmetric respect to the x-axis. So you have to keep testing. Oh, I ate an N. No symmetric respect to the x-axis. Now you test if it's if it's symmetric respect to the y-axis. For that you have to change x into negative x. So I write my equation, but instead of x I'm gonna have negative x. Oops, I don't think you can see that. Okay, sorry. So you test for symmetry around the y-axis, you change x with negative x, and then you simplify and see if you get the same. Remember that we did this before. This is just negative x cubed, and negative 9 with negative x becomes positive 9. Now you compare this with the original and see if you get the same. The original is y equals x cubed minus 9x. So this doesn't look like did I do the same? Okay, yeah. It doesn't look like the original, so this is not symmetric again, respect to the y-axis. So we tested those two, and now we just need to test the last symmetry. So test for symmetry around the origin. So you're gonna change x with a negative x and y with negative y and see if you get something that is equivalent. So negative y equals negative x cubed minus 9 minus x. From the previous test, I know that this becomes negative x cubed plus 9x. And now I have to divide by negative 1. So you have, I'm going to write it over here, y equals negative over negative is positive, and positive over negative is negative. And you see how you obtain the original equation. So this is symmetric respect to origin, which is actually good because we're gonna get some positive values and then we're gonna reflect them over the origin. So I'm gonna have my sketch over here. I'm gonna have a few values. Let's pick 0, 1, 2, 3, 4. So now when x is 0, I'm gonna do 0 cubed minus 9 times 0, and that's 0. So that's a point on the graph. Then when I replace with 1, I'm gonna have 1 cubed minus 9 times 1, and that is negative 8. And then I'm gonna graph that. And then when x is 2, 2 cubed minus 9 times 2, and that will be 8 minus 18, negative 10. And then 3 cubed minus 9 times 3, and that will be 0. And then when x is 4, 4 cubed minus 9 times 4. 4 cubed is 64, 9 times 4 is 36, and then that will be 64 minus 36, that will be 28. Okay, over here. So my graph is gonna go like this. Now, since I know that it's symmetric over around the origin, then the only thing I have to do is find out what are the inverses of those. So if I know the point 428 belongs to the graph, I know the point negative 4, negative 28 belongs to the graph. If I know the point 30 belongs to the graph, I know negative 30 belongs to the graph. If I know the point 2, negative 10 belongs to the graph, then I know the point negative 2, 10 belongs to the graph. In here I have 2, negative 10. If I know the point 1, negative 8 belongs to the graph, then the point negative 1, 8 belongs to the graph. and then if the point 0, 0 belongs to the graph, then 0, 0 is the same. So I can see now how there is a symmetry in respect to the origin. This piece, if I draw it and then I turn it around the origin, is going to overlap with this other piece. And that's how I test for symmetry, and that's how I use that symmetry to sketch my graph in an efficient manner.